With growing demand for better audio quality in portable devices such as mobile phones, headphones, and audio streaming devices, it became obvious that the 8 kHz bandwidth of the traditional 711 coupler was insufficient, and a new approach was required to match the acoustic impedance of the human ear over the full audio range. Initial research indicated that the simplistic geometry of a Type 3.3 ear simulator would not be able to duplicate the complex acoustic impedance of the human ear to 20 kHz. A more human-like geometry was required. The problem is, of course, that every ear is different. So how do we define a practical shape that would be representative of the average human ear? You determine the average geometry and impedance. The pursuit of an average geometry started with MRI scans of more than 40 volunteers from a range of ages, ethnic groups, and both sexes. Preliminary MRI scans did not yield good data as the ear canal walls were not clear in the image. This issue was solved by the addition of a contrast agent to the ear canal, which allowed sufficient image quality for accurate characterization of the ear canal. From the MRI scans, they were able to create accurate 3D representations of the ear canal geometry, which could be converted into a solid geometric model. While the overall shape of the subject's ear canals were generally similar, the variability of detail between the subjects was significant. Geometry averaging using the image registration method was used to determine the mean profile along the length of the canal, resulting in an average 3D model used as the basis of an ear canal design. Here, the geometric average is compared to one of the measured subjects. As you can see, the average retains the key characteristics of the individual measurement, but smooths out the more random details. The second step in the process was to determine the average acoustic impedance. This required the application of a specially designed impedance probe which required precise positioning in the ear canal. To do this, individual earplugs for each subject were molded using extracted geometries from the MRI measurements. Each plug was designed to position the probe as close as possible to a common reference plane 19 millimeters from the eardrum. The impedance probe itself was created using 2 probe microphones, one to measure the response and the other adapted to act as a sound source. A coiled tube in the measuring probe housing provided for a smooth frequency response and a high acoustic impedance at the probe tip. The tips of both probes were mounted flush with the bottom of the ear molds, and with the right calibration and a little math, the impedance of the middle ear could be measured. Despite best efforts, the position of the probe tip from subject to subject was not exactly 19 millimeters, and the variation in the distance from the probe tip to the DRP, the drum reference point, resulted in the resonant peaks in the measured impedance curves being smeared. However, using transmission line theory, it was possible to calculate the correct impedance to simulate the result at the 19 millimeter common reference plane. The resulting data provided a family of impedance curves which could be used to get an average curve. To reproduce the increased complexity of modeling the correct impedance above 10 kHz required a redesign of the coupler with a 1/4-inch microphone to match the size of the human eardrum. The number of vents, known as branches, was increased from 2 to 4 to allow tuning of the resonance peaks and associated damping. A further complication was to try to mimic the transition from soft tissue to the bonier condition nearer the eardrum. By modeling and testing various materials and techniques, the transition was optimized for smoothness and robustness. Several iterations of tuning produced a close match to the average measured impedance from the subjects and well within the engineering tolerances that were the target for the response. The final step in the puzzle was to tune the open ear response and integrate into the hat structure. The pinna geometry was carried across from the version standardized in ITU P58, but to match the frequency and damping of the earlier standard, the concha had to be increased in depth slightly. The final result is a new design of hats that can accurately measure the response of near-field audio devices to 20 kHz. Almost as importantly, the human-like ear canal geometry can more effectively test in-ear devices fitted correctly.